All right, we're going to look now at the derivative of the natural exponential function, or in other words, we're going to look at the derivative of y equals e to the x. We're going to look at this graphically to start with, and we're going to use a graphing calculator first, and then later use some software to get a little bit more dynamic look at it. So first on the calculator, we need to enter our function. Y equals e to the x. You need to find where your e button is on here somewhere. There's that one. And what we're going to do is get it to graph the derivative. Now, if we don't know what the derivative is, with various technology, you can get it to do what's called the numerical derivative, which is it just calculates the slope really close at points as it goes across the screen. So it's not doing calculus or anything like that. It's just going to calculate slope. All right, so on this particular calculator, you find the numerical derivative the quick way under that menu. Or you can go find it under that math button. Now what we wanted to do here is we want to find the derivative with respect to x of the function that I have in y1. I could just put e to the x here, or I can put in, I wanted to do the derivative of what's in y1. And normally when you use numerical derivative, if you're just calculating the derivative at a point, you'd put a number here. Say you want the derivative of some function at x equals 3. You put a 3 there. I wanted to graph the derivative. I wanted to calculate the derivative at every point across the screen as it's graphing. So I want this to be a variable. I want it to change as it goes across the screen, so I need to put an x in there. All right. Now for my window, I'm going to start with just this zoom decimal because that's a good enough window. And we'll see what we get here. Now it's going to graph that function, and it's going to graph the derivative. It's doing some thinking because it's working with calculations. As it graphs the numerical derivative, it takes its time because it's a lot more tedious, complicated calculation at every value. And then it stopped thinking. We can't see where the derivative is. Where do you think it is here? Well, we're going to change a few things and then see if we can see what's going on. First of all, we don't need all this space below here, right? Because the derivative is positive every time, right? The slope is sloping uphill, right? This thing's going uphill. It's never going downhill, so the derivative is never going to be below here. So I'm going to get rid of that part of the window. I'll leave it a little bit just so that the axis is not right at the bottom of the screen. Maybe we'll put that at 5.1. And the other thing we're going to change is we're going to make this a thick line, and then we'll see what's going on here. So it's going to graph our function e to the x, and then hopefully we're going to see the derivative starting out over there. It's following that line. Look at that, it's following that line. It's following it all the way. So what does that mean? What does that mean? That derivative is right on the same curve as the original function. Well, I'll tell you what that means. Let's think about at any single point here. If we trace along to any single point here. So let's trace over to, say, make it easy, x equals 1. X equals 1, e to the x. If x equals 1, that y value of the function should be e, right? That's what that is. The y value at 1 is e. If this derivative is exactly the same curve, what it's also saying is the slope of the tangent line there is also that value. We're going to look at that using some dynamic software in a minute, but for right now we should just probably write down that if you have that function, the derivative is e to the x. It's its own derivative. If you wanted, you could write the second derivative as e to the x, third derivative is e to the x. It just keeps going, right? We go down here, e to the x. It's its own derivative. That's going to be probably the easiest derivative you're going to have. You're going to have the easiest time remembering that one. It's its own derivative. But it's important also to understand what that means. All right? So let's look at it in a more sophisticated way, as I had mentioned we're going to do. Using some graphing software, we're going to graph, call this f of x, and that's going to be e to the power of x. There's the function. Let's change the color of it so we can see it a bit better here. There we go. Now we're going to put a tangent line on this curve. Put a point on there first. Let's make it so we can see the coordinates of that point. There we go. And we're also going to now draw a tangent at that point. Tangent at that point on that function. There we have a tangent. And let's change the color of that too. There we go. Now, so the comparison here we're making is we have this equation of that tangent line in slope-intercept form, 1.84x plus 0.72 right now, and there's the point. Just a random point that I put on the curve somewhere, but you see here again, the y value matches the slope of that line. As I slide along here, move this thing, they both change, right? Anywhere I stop here, 1.22, 1.22. Think about what's happening. Let's go right to the middle. The slope of that line, you can see, is 1, and the y value is 1. As I go off to the right, the y value is obviously increasing, and the slope of the curve is obviously increasing, and they exactly match in this function. If I go to the left, right, the slope of the curve is decreasing. It's getting flatter and flatter, and the y value is also decreasing. They exactly match over there too. Everywhere on this curve, the y value matches that slope. That's an important piece of understanding to have, what it means to say that e to the x is its own derivative. All right, it means the slope of the curve matches that y value anywhere on that curve. You can even put in here f prime x, and it'll graph that right on top of the other curve. The blue, the black, same function. All right, so let's just draw a quick picture of this before we move on to something else. Let's draw that curve. Goes up pretty steep there. You can draw the tangent line somewhere. I didn't obviously draw it perfectly, but you get the idea. If we have some x value here that we're going to call a, then this value here is e to the a, and the slope is e to the a. All right, so the significance here is slope equals that y value, or in other words, the function value, right? Function value is the same as that slope, all right? Now, I wrote down a question here that I wanted to think about. Can you think of any other functions that are their own derivatives? Any other function that has itself as its derivative? Well, I can think of a few things here. None of them are going to be any more interesting than what we've already got, because one of them is just any constant multiple of e to the x. All right, like if you have y equals 7 e to the x, and we want to take the derivative of this. Derivative of that is just 7 times the derivative of this, right, which is 7 times e to the x. So it's its own derivative as well. And then the only other thing I can think of is just y equals 0, right? Y equals 0 is just a horizontal line along the x-axis. The slope of that, of course, is 0, right? So if y equals 0, y prime equals 0. All right, so more or less, this doesn't mean anything on top of what we already know here. The fact that e to the x is its own derivative is interesting. This maybe not so much. All right, so that's a look at how e to the x is its own derivative.